Here we want to take a look at a function y equals f of x defined on a closed interval from a to b. So it looks something like this. And what's our goal? We want to wrap this function around the x-axis, creating a solid. And then our goal is to determine the surface area of that solid of revolution. Previously, we've done volumes of solids of revolution. Here we're going to do a surface area of the solid of revolution. So what is our strategy going to be? We're going to break this up in multiple pieces and see what happens as we wrap those around the x-axis. So again, there's our original function. Here it is broken into pieces. So to try to visualize this, I put a point here, a point here, a point here. So now I've broken this curve into 1, 2, 3, 4 different pieces. And instead of wrapping the curved piece, we're going to wrap this secant, this straight line. If I wrap that straight line around the x-axis, geometrically, what do we get? What will that shape be? Again, think about if I wrap this straight line about the x-axis, what will that shape be? If I wrap this straight line around the x-axis, what will that shape be? Well, there we go. There's our image. What is that image? What do we have? Well, there's 4 line segments that have been wrapped around, and we have these 4 pieces. They are all frustums, portions of cones. So we have a cone portion on the bottom, and then it's missing the cone portion on the top to make the entire thing a cone. So indeed, multiple frustums as I wrap each of these things around the x-axis, the result is a frustum. So currently I only have 1, 2, 3, 4 of them. So if I find the surface area of these 4, that will give me an approximation for the surface area that we would get for rotating this curve around the x-axis. And then we're going to go ahead, instead of just looking at 4 frustums, we'll look at an infinite number of them, where the difference between these points gets smaller and smaller, shrinking to 0. So the total surface area, again, is the sum of the surface area of the frustums. That's what we're saying. So here is a frustum. Big R is what I call the radius of the larger portion that we typically visualize as sitting on the bottom. Small r is what we think of as the radius of the smaller portion, the smaller circle that makes up the frustum. The height distance from the bottom of the frustum to the top. And then the slant height L is here. And it is a challenging exercise, and I encourage you to watch my other video to prove this fact, that the surface area of a frustum is pi times L times the bigger radius plus the smaller radius. Pi RL was the surface area of a cone. So it's kind of interesting that pi LR plus R is the surface area of a frustum. Except there's a version we're going to be using here that's a little bit different. Namely, I'm going to replace R plus R with 2 times R plus R over 2. So you'll notice those 2's would cancel, giving me this. But if that's the case, then what is R plus R over 2? R plus R over 2 would simply be the average of the 2 radii. The big R plus little r over 2, the average of the 2 radii is what I'm going to call that. I'll have 2 pi L times the average of the 2 radii. So that's our formula for the surface area of a frustum, or what we're going to want to look at. We need to decompose our curve into multiple pieces, find the surface area of each frustum, and then add them together. We're going to add an infinite number of them together using integrals, as we've done with our volume and arc length questions before. So here's a question we're going to look at. We want f of x to be the square root of 25 minus x squared, defined on the interval from -5 to 5. We want to find the surface area of this solid obtained by revolving this curve about the x-axis. Let's try the x-axis first, and then we'll try the y-axis to see if the results are the same. So what are we doing here? There's our curve. We're going to wrap this thing around the x-axis. I want you to imagine putting dots to subdivide this into several smaller pieces, and then connecting line segments between them to create the frustums. Now, what is that going to look like? Here's one of the partitions, but imagine I have many, many more. Now, what will that frustum look like? Imagine wrapping this piece of the circle, which we'll actually consider a straight line in our case, wrap that around the x-axis. What will that frustum look like? And we get something like this. So here we are at this image. We need to determine what is the surface area of that piece, and then eventually sum up all of them to find the surface area for all of the pieces. Now, we will need the arc length of this piece. So what do we remember? The arc length of this piece of the curve will be the slant height of the frustum. There will be capital L that we are dealing with. So we're going to need that to get the surface area of the frustum by having the slant height of that frustum. So this is our notion. Now, what was our function? It was f of x equals the square root of 25 minus x squared. So that would be the same thing as saying y equals 25 minus x squared to the 1/2 power. In which case, then what is dy dx, which I will need for this? What is dy dx? 1/2 times 25 minus x squared to the 1/2 minus 1, which is negative 1/2, times the derivative of the inside, times negative 2x, which is going to give me 1/2 times negative 2x, negative x, over the square root of 25 minus x squared. But I need dy dx squared. So negative x times negative x, positive x squared. What's on the bottom? Root 25 minus x squared times root 25 minus x squared. 25 minus x squared. Continuing with this, I need the square root of 1 plus dy dx squared. Which is 1 plus x squared over 25 minus x squared. Getting a common denominator is 25 minus x squared over 25 minus x squared plus x squared over 25 minus x squared. And what do we get? We get 1 plus 25x squared plus x squared is 25 over the common denominator 25 minus x squared. Well, that's useful for me, but you'll recognize, what do I need? I need the square root of that for my arc length. So what can we say about that? How can we make sense of that? So the arc length will be what? Square root of 1 plus dy dx squared dx. The integral from something to something of the square root of 1 plus dy dx squared, which is this, square root one plus dy dx squared is 25 over 25 minus x squared dx. Make sure we know this radical goes all the way down to the bottom. So that's my integral from a to b of root 1 plus dy dx squared. There's 1 plus dy dx squared is 25 minus 25x squared. Put a square root in front of it, and we get this. So this is our current arc length portion. So if arc length is the integral from a to b, root 25 is 5 over 25 minus x squared, square root of dx. So we have that portion, we have the L portion, kind of. But remember, what do we need? We need the surface area of the frustum. Which was what? Which was 2 pi L, so this part is essentially L, times the average of the radius. So we need to think about what the average of that radius is going to be. So you need to see this as a frustum. One of the radii is here, and the other of the radii is here. So they are values of the function. The value of the function at 4 is my smaller radius. the value of the function at 3 is my larger radius. So I'm looking for an average. Well, remember that what's going to happen is we're going to make finer and finer and finer partitions so that eventually these things are going to come closer and closer and closer together so that the little r and the big R are basically the same. So what do we want to think about? As these things get closer and closer together, pick some value x. The radius for that value x would be f of x. If I move it just a little bit off, it would also be pretty close to f of x. So that's in essence our idea. So let's formalize that a little bit. So we imagine partitioning this function into several pieces. We're going to make frustums on every mini interval. So I just happened to pick this one, and I'm calling this value x. Can you see how the radius from the center of rotation to the frustum, it's essentially f of x here. It's a little bit less than f of x there, and it's a little bit more than f of x there. So what is my approximate average radius? One's a little bit more than f of x. The value of the function at this x is a little bit less. That one's a little bit more than what the value would be if I was directly in the middle. So the average radius is in essence here just the value of the function at x. That's what we're working with for our average radius. Again, try to see it. F of x would be here. We're making a little strip on either side. So the smaller radius is a little bit smaller than f of x, the bigger radius a little bit bigger than f of x. So we have our formula here. Surface area of the frustum is 2 pi times the arc length times the radius, average version. What was my function for f of x? F of x was the square root of 25 minus x squared. So can I put this together? What will the surface area of my frustum be? It will be an integral with a 2 pi. The L part before was from a to b for our interval, but this time we're going to go over the entire interval, which is from -5 to 5 as we add all of these frustums together. From -5 to 5, we'll add all of these together. This is the portion that I needed for my arc length, which is 5 over the square root of 25 minus x squared dx, but I'm going to hold off on the dx until the end. And then what is my average radius? My average radius, we said, was f of x, which is indeed root 25 minus x squared dx. So this is the format that we get for evaluating this when we rotate this thing about the x-axis. So let's quickly evaluate this. What is that going to give me? Copying it again, we have the surface area, total surface area of the solid of rotation is the integral from -5 to 5 of 2 pi times 5 over the square root of 25 minus x squared times the square root of 25 minus x squared dx. And you'll notice that the square roots divide out, and we are just left with 5 times 2 times pi, so that's what, 10 pi. We have the integral from -5 to 5 of 10 pi dx. Notice how nicely this turned out. In reality, surface area integrals are almost always impossible to evaluate. We were just extremely fortunate here to get one that worked out well. My antiderivative would be 10 pi x, evaluated as x goes from -5 to 5. So the surface area is 10 pi times 5 minus -5. 5 minus -5 is another 10 times that 10 pi gives me the surface area of 100 pi. But remember what we had. What was our shape? What were we looking at? We had this thing. If we're going to wrap it around the x-axis, the result will be a sphere. And you may know the formula for the surface area of a sphere. Let me remind you of those facts. The volume of a sphere is 4/3 pi r cubed. The surface area of a sphere is the derivative of that, believe it or not. Think about why that might be the case. 4/3 times 3 is 4 pi r squared. So in our case, what was the r? What was the radius? In our case, from the center out, the radius was 5. So indeed, our radius is 5. In our example, radius is 5, so the surface area of the sphere is 4 pi times 5 squared, 25 times 4, 100 pi, which makes me very happy.